In this video, we are going to work through an exercise with a second-order Taylor polynomial for a function which is a scalar valued function of two variables. This function is not very interesting. What we have here is f of x and y equals y times e to the x. So this function has no motivation or story behind it. It's just the product of a polynomial and y times the exponential function e to the x. So this example is really just a toy example to work through an exercise in class. It's not motivated by anything scientific or something like that. However, I would really like for you to watch this example all the way through to the end, because along the way, I'm going to mention some algebra steps, some thought processes that you should go through whenever you are evaluating both the linearization or the second order approximation for a nonlinear function, as we are doing here. So while this function is a pretty basic function, it's obviously smooth. As I mentioned, it's the product of a polynomial and an exponential function. We don't need to check if it's C2. It's going to be smooth. So while this example feels like a small example, I hope that it will give you some ideas going forwards of what to look for when you're doing this kind of exercise. We would like to write down the second order Taylor polynomial for f of x and y equals y times e to the x. For that, we need first the gradient. Let me jump straight to computing the gradient at the point a, b. So here, a and b are fixed numbers. This function is defined on all of R2. I didn't want to be more specific than that, but we imagine that we are fixed at some point like -1 and 2. Okay, at AB, our gradient is a vector with two entries. And I will write this down. I could plug in A and B immediately, but let me show you how to do this if you're still kind of differentiating before you're ready to evaluate. So we need to take the derivative with respect to x. That's going to look like y e to the x. And then take the derivative with respect to y. That's going to give us e to the x. Here I've got x and y. Here I have A and B. So what you can do is put in an evaluation bar to say, we're going to evaluate this at that point. Let me plug in x equals a, y equals b. And as I do so, one strategy whenever you're working with vector valued expressions in math is to try to factor out as much as you can. So let me pull out the scalar quantity e to the a so that we have b and 1. Okay, that's one term we need. Let's do the Hessian matrix now. And again, I'm going to go ahead and say that we are doing this Hessian at the point AB. Because our function is smooth at C2, so it is smooth and also at C2. Those aren't equivalent notions. I know my Hessian is going to be a 2x2 symmetric matrix, so make sure that your matrix is symmetric. If it's not, something went wrong. To compute a Hessian, what you want to do is grab this and differentiate it with respect to x and y down the first column. So with respect to x, we're going to have y e to the x. With respect to y, e to the x. Now differentiate this with respect to x and y. We'll have e to the x and 0. But we need to evaluate that at the point AB. I switched markers and I don't think this one is as good. I apologize. I hope it's still readable. Once again, in vector calculus, if you can pull a scalar in front of a vector quantity, or in this case, a matrix quantity, do so. It usually makes things better. So let's pull what will now turn into e to the a in front. And we will have b, 1, 1, 0. And yes, it is symmetric. We need now to write down the second order Taylor polynomial for this function centered at the point AB. We have the components that we need. So let me write this down. It's not a very long computation so far, but I'm almost out of room. So I hope I can squeeze this down here in a way which is readable. So the second order Taylor polynomial, it's a function of x and y. The idea here is that x and y are near a and b, so that this polynomial is an approximation for f, which is reasonable near a and b. If we're very far away from a and b, we shouldn't use it. Okay, it is the function evaluated at ab. So that's going to be b e to the a. So that's f of a and b, plus the gradient dotted with the difference factor xy minus ab, so x minus a, y minus b, like that, plus the term students often forget, and honestly, I do too. 1 over 2 factorial. It's just one of those things that sometimes you leave out. And now we need to write that second order Hessian computation. Remember that the Hessian matrix is a bilinear form. It acts on pairs of vectors. And we talked about what it looks like when it acts on a pair of vectors. What we're going to do, this is the vector, by the way, it's going to act on this paired with itself. And how that's going to look is we take the transpose of this vector. Now, whenever I write a vector like this, with parentheses and commas, like it's a two-tuple in this case, or an n-tuple in general, I mean for this to be a proper vector, which is always a column vector. So I'm going to transpose it, and what I'm writing here is literally a 1 by 2 row matrix. So that's my notation. This is a 2 by 1 vector. This is a 1 by 2 row. Okay. That times the Hessian, I have this leading e to the a. Let me see if I can squeeze that right here. Kind of forgot about that. So I've got e to the a as a scalar. Pull that out front. And now we have b110. And then for this matrix product, it's going to look better if we write the other vector as x minus a, y minus b, as it really is. So this in proper vector form, x minus a, y minus b. Sorry, that's y minus b. This is our second order Taylor polynomial, but in my opinion, it doesn't look that good because I've got a dot product. I have a matrix triple product here, and it really should be a scalar valued expression. It is a scalar valued expression, but I think it could be written in a way which is a little bit more accessible at first glance. So let me pause and take a moment, make sure you've written all this down. When I come back, I will have erased what we have up here, so the gradient and the Hessian, and I'm just going to show you how to expand this in a way which is very useful. In particular, this matrix triple product can be done quickly and efficiently. I say that because sometimes I see students look at this kind of thing for the first time and they start kind of multiplying these two together, kind of term by term, and then they bring this in, and there's a way to just immediately knock it out. So I'll show you how to do that in just a moment. Okay, it's a little strange to simplify up, but if you permit me, I'm going to rewrite this expression up here. And let's just expand this. That's what I wanted to get to, is something that looks like a second order polynomial for the variables x and y. Okay, we have this leading scalar b e to the a plus e to the a. I'll go ahead and expand this. So how about bx minus ab, there we go, plus y minus b, like so. Now, here's what I want to do carefully. Let me leave this scalar out front. So we have e to the a over 2. With this nice symmetric Hessian triple product here, there's a way to think about how these terms will multiply together that allows you to do the triple product all at once. So instead of multiplying 2 matrices and then a third, you can do all of this at once. And that is to recognize that the first term in this vector will partner up with the first term in this vector with the b entry in the matrix. So it's like the only way for this term to meet that term is if they've kind of passed through this b. Similarly, the only way for y minus b to meet y minus b is through the 0. And then the mixed terms, x minus a, y minus b, and y minus b, x minus a, those meet through the 1, 2, and 2, 1 terms. So it's like, how do these expressions encounter each other in this triple product? The coordinates in the vectors pair up with the indices in the matrix. So like 1, 1, 1, 1. Okay. And that's valid anytime you multiply this kind of, vector times matrix times vector, but it works really well with the Hessian here because everything is symmetric. So we're going to have, I'll leave it as e to the a over 2 times b times x minus a squared. Okay, b x minus a squared. Now we will have 2 instances of x minus a pairing with y minus b. So here, and both of those meet with a 1. Okay, so it's going to be e to the a over 2 times twice, all right, 1 So 2 times 1 times x minus a, y minus b. And then lastly, we have 0. Okay, that's good because I'm out of room. All right. Let's clean this up a little bit. You'll notice that all of the terms have an e to the a. They don't all have a b, so let me just pull e to the a in front. At this point, it's just going to be algebra, which means that we run the risk that I'm going to make a mistake here. So let me write down the best that I can do, and then we will check our answer before we move on. So b plus bx minus ab plus y minus b. I'm just going to go ahead and do this. Okay. Moving along. Plus, trying to think if I want to expand these quadratics, and I have decided that I do. So b over 2x squared plus b over 2 times negative 2ax, so the 2's will cancel, plus b, no, minus, oh, so much risk here. I have this written down over there, so I will check myself at the answer. Minus b a x, I think that's right. And then plus e to the a, no, that got factored out, b over 2 times a squared. Okay. Yeah, that seems right. All right, the 2's cancel here, that's great. E to the a, no, e to the a got factored. All of this is just 1. Xy minus xb minus ay plus ab. Okay, let's step back and see how we're doing. One reason why I wanted to expand it, having done this computation before, is things cancel. So we already canceled this. This will cancel with that. That's great. Anything else? Ex will cancel with bx. Y bx squared over 2. These are all quadratic. I think that's what we're left with. The next question to ask ourselves is, how do we compare this to this function f, which is y e to the x? So I want to show you how you can compute the error between the function that we started with, which was not a polynomial, and this degree 2 polynomial. So what are our attack strategies so that we can say, is this a good approximation near AB? In particular, we want to check that the remainder, which I will call r sub 2 to pair up with t sub 2, is little o of xy minus ab squared. So in other words, I'll show you what that means if that doesn't ring a bell, but we will check that the remainder vanishes suitably fast. It will, because this function is nice and smooth. It's going to be well approximated by its Taylor series near AB, meaning it's going to satisfy the necessary limit, but I'll show you how to do the algebra to back up that statement. Okay, take a moment, if you haven't, to make sure that you either have this, or if there's a mistake, which there might be, you have something correct. I'll come back and after having proofread this, and we will move on to looking at the error term between our function and our polynomial. Turns out I had it right. So this is the expression that we now need to evaluate. So we are looking at the error between our original function y e to the x and the second order Taylor polynomial for our function centered at the point a, b. So how do we compare this kind of function, which is a product of a polynomial and an exponential function, to something which is just a polynomial? Like, what kind of cancellations can we do here? At first glance, the answer is nothing. So we need a strategy. And here's what it is. We are near the point A, B. So the most complicated part of this problem, the reason why it doesn't feel like something we can immediately work with, is because of this exponential term e to the x. It's the only thing on this board here which is not a polynomial piece. We are near A. So e to the x is near e to the a. We could think of that a little bit differently as x minus a is near 0. Okay, so what could I do with this exponential? Now, assuming, we're looking at a Taylor series for multivariable functions. So I'm imagining that in your background, you've worked through Taylor series for single variable functions, in particular, the Taylor series for just the plain old exponential function e to the x centered at, say, 0, something you could call the Maclaurin series. And that is exactly what we are going to do. We are going to take our exponential piece, e to the x here, and handle this by bringing in the Taylor series expansion for the exponential function. I think the best way to do this is actually to factor e to the a out of everything. So I'm actually going to do this not while you're watching me so that I can like write it very neatly, but I'm going to take both of these pieces here and pull e to the a. In fact, let's make it e to the a over 2 so that we get rid of these denominators. Pull that scalar quantity in front of this difference. E to the a will just factor out of itself, leaving us with 1. But here we'll have e to the x minus a after we factored e to the a out. So it's like e to the x divided by e to the a is e to the x minus a. Then x minus a is close to 0, since x should be close to a for us to be even evaluating or estimating how f behaves with this Taylor polynomial. So since x minus a is close to 0, e to the x minus a is close to e to the 0, and then we're working near the center of the standard Taylor expansion for e to the x. Okay, that was a lot of words out loud. That's a preview of what's to come. Let me step aside for just a moment, and when I come back, I'm going to have written out just exactly this, but with e to the a over 2 pulled out in front, just so that it's nicely written. And if you'd like, you can pause and just go ahead and do that on your own. All right, we're ready to go. All I did was factor this constant in front. I made a few sign errors and dropped some 2's along the way, so I'm glad I didn't record that. But this should be what we are working with now. And this is the piece that we need to tackle. X minus a is approximately 0, so this is approximately e to the 0. We are going to estimate this using the Taylor series expression for, let me call it e to the u, centered at 0. So that's approximately 1 plus u squared over 2 factorial plus u cubed over 3 factorial plus u to the 4th over 4 factorial, etc. We don't need all those pieces. I'm going to say that this piece here, let me write it in orange, is approximately 1 plus what I called u a moment ago is x minus a, plus that squared over 2 factorial. I'll just write 1 over 2. How about just 1 over 2? That's what 2 factorial is. X minus a squared plus 1 over 3 factorial times x minus a cubed. But I claim this is enough for us to continue on. This is what we need. So you could write higher order terms. Sometimes I write that. I'm going to write big O x minus a, that quantity cubed. Okay, so the idea is that this factor here is present in all of the other terms. You could factor it out, kind of governs the behavior near x minus a equals 0. Right, so that's our big O notation. Let's now keep going. So we leave the scalar out front. And I'm going to take this expression, replace it with this, and also multiply by 2y at the same time. So we'll have 2y times 1 plus, let me distribute 2yx minus 2ya. The 2's will cancel in the next product, so 2 times 1 over 2 times y. And then okay, so from this we get a y, and I'm going to expand this because everything else is expanded. So how about y x squared minus 2yax plus ya squared plus 2y times the big O notation. I'm just going to write fancy O because I'm almost out of room. I'm also going to drop down to the next line. Do I need to? Let me start canceling things. No, let me just drop down. Sorry, it's not a complicated, we're just working with polynomial pieces. It's just a big expression. So we're just going to copy this all down. So 2y minus bx squared plus 2abx minus a squared b minus 2xy plus 2ay. This marker is ready to move on. Okay, now we have some cancellations. Let's knock some of these out. So 2y and 2y. 2yx, so plus minus 2ay with a minus and a plus. Is that everything? Yx squared. I think so. So actually, it was silly of me to do this. Let's just bring that back in. Oh yeah, this is a nice marker. Okay. Let's see. I think everything is canceled. But you see, the beauty of what we did with this replacement is that we replaced an exponential function with something polynomial. And now we are ready to keep going. So what we're going to do next, I'm still looking, okay, yeah, I'm satisfied, is start, well, I want to say that this expression is going to go to 0, first of all, and it's going to go 0 faster than, say, the quantity x minus a squared plus y minus b squared. I'll set up that limit a little later. Let's keep simplifying here. Okay, we have yx squared, ya squared, 2yax. Maybe I shouldn't have distributed this. I'm going to write that back as yx minus a squared. Okay. And then here, this looks like minus b x minus a squared, and then plus 2y times the higher order stuff. Cubic terms and beyond. So let's see, these three terms factored like this, these three terms factored like that. And you can even take this further, because here we could write this, write it one more time, and then I'll erase everything. This is really x minus a squared times y minus b plus 2y times higher order terms. Okay, I think this is the form that we want to compare our function to the Taylor series polynomial that we wrote down in order to get a sense of the error. In particular, we want to measure how small the error is close to x equals a, y equals b. So we are going to take this, which is our error, and set up a ratio for it that satisfies what we need in order to say that our function has been well approximated by the Taylor polynomial. I don't want to say it out loud. I'm going to write it down in just a moment. In words, let's just look at this. X is going to A, Y is going to B. So both of these factors are going to go to 0. X is going to A, this goes to 0. Y is going to B, this isn't going to 0. This is going to 2 times Y is going to 2 times B. But when you look at both of these terms, this is ultimately like a degree 3 going to 0. So we've got quadratic and a linear or first order expression. So here the product of total 3 factors, all of which are going to 0. This is big O x minus a cubed. So there are infinitely many terms kind of hidden in this expression, but all of them are cubic order or higher. We're going to compare it to an expression which is going to 0 at like a quadratic level. So yes, this will end up dominating that ratio. Everything will be satisfied. I just want you to take a moment to appreciate the form of the expressions left over. So we've got terms which are going to 0 and going to 0 at like a higher order than, perhaps when we worked with a first order expression. All right, in a moment, I will come back. All of this will be erased, so make sure you have it down. And we will set up the limit that we want to compute in order to verify that, yes, our function is being well approximated for a degree 2 approximation near AB. That's pretty quick, especially because we've already put it in the right form, the form that we need to work with. I have one thing left for us to do, and that is to prove that the remainder expression that we just worked out is what's called little o of the distance from xy to ab squared. So that reminds us of Peano's form of the remainder from Taylor's theorem. And the general statement is that the remainder associated with the kth degree Taylor polynomial is little o of that distance to the kth power. So here, since we were looking at the degree 2 Taylor polynomial, we have the distance squared. What does little o of that distance squared mean? It means basically that the remainder is much smaller than that. So that's kind of like a qualitative understanding of that notation. Quantitatively, if I take the remainder and put it in ratio with that distance squared, and then I let x and y go to a and b, you'll notice that this ratio is an indeterminate form. Both the numerator and denominator are going to 0. For the remainder to be little o of the distance squared, we would want to see this entire quotient go to 0 as x and y go to ab. So it's like the remainder not only goes to 0, but it goes to 0 so quickly that it dominates the behavior of this expression and drives the whole thing to 0. And then here, just to the right, to save us the first step, I've gone ahead and put in the explicit form of the remainder that we just worked out. Let's evaluate this limit. There's not too much left to do because we did so much simplification a moment ago. I just want to remind you, kind of like another lesson in this kind of toy Taylor series example, that if you're taking a limit in the xy plane, you might want to consider switching into polar coordinates. So we have a 2D limit. X and y are going to A and B. I'm going to switch into polar coordinates. Just make sure that you center your polar coordinates at the point AB. So it's not x is r cosine theta, but rather x is A plus r cosine theta, and y is B plus r times sine of theta. That way, as the radial coordinate r shrinks to 0, x goes to A and y goes to B. We have two coordinates here, r and theta. So another quick reminder is that while we are going to let r go to 0 so that x and y go to A and B, theta is an angular coordinate, and you don't know how theta behaves in this limit. It could be a constant, but it doesn't have to be. If you're spiraling in on the point AB, you would think of theta as changing like a function of r. So do not try to do anything with theta when you do this kind of conversion into polar coordinates. Leave it inside the limit, treat it kind of like an unknown function of r, because that's essentially what it is. Okay, let's take this limit now and convert it into polar coordinates. Might have a lot to write here, so I hope I can fit this all in one line. We have e to the a over 2, that's just a constant. X minus a squared, notice x minus a is just r times cosine of theta, so we will write r squared and then the square of the cosine. Y minus b likewise is r sine theta, so r squared times r. Let me adjust this into an r cubed. There we go, r cubed, sine of theta. Plus 2 times, it's tempting to just write y, but let me put this whole expression in. As r goes to 0, that's just going to go to b, but we'll have b plus r sine of theta. Okay, I think I can fit this in here. And then little o of x minus a cubed. Okay, bring a over again. I'm going to write little o of, big O. There, it's big O notation now. X minus a cubed, I'm going to write r cubed cosine cubed, although it's the r cubed that we really want to focus on in this example. So this is an O. Okay, big O of r cubed and then cosine cubed. Okay, I think that's all the parentheses. Fairly straight line. For the denominator, don't start plugging in and squaring and adding together. It's the distance from xy to AB squared. Well, the distance expressed in polar coordinates is r, so we just have to write r squared. Okay. And at this point, we're basically done. The question is, how much more do we want to write? Notice these two expressions, r squared will divide into them. So I'm going to take r squared and divide it into r cubed, leaving us with r. And then here, it's going to divide into this r cubed. So keep in mind that there are infinitely many terms inside of this big O notation, but all of them have at least r cubed and actually higher. So if we expanded this, we would see r cubed, r to the fourth, r to the fifth. R squared will divide into all of that. So I will change that big O notation into it's big O of r and cosine cubed, but the r is what's really key. Yeah, I'll write this one more time. It's the end of this lesson. So we have the limit as r shrinks down to 0 of this constant number e to the a over 2 times r cosine squared theta sine of theta plus 2 times this, which doesn't vanish, it goes to b, but that's okay, times big O of r cosine cubed. Okay. These trig terms are bounded, right? So each one is bounded between -1 and 1. So cosine squared between 0 and 1. This goes to b. This vanishes. So overall, this is 0. And that's what we wanted to see. Okay, so to recap, we had a function which itself was not very interesting. F of x and y is y e to the x. It's made out of two very nice pieces. But what I hope that you got from this video, so what the take-home messages are, is just how to set up that second degree Taylor polynomial. So you need the gradient, you need the Hessian, write it out. And then if you hadn't seen it before, I hope you found it rewarding to see how the matrix triple product can be quickly evaluated. So if you really understand what that row times the symmetric matrix times the vector, that piece, I hope that was rewarding for you. So we computed the Taylor polynomial, and then probably the most useful aspect of this demonstration was seeing how we actually brought a Taylor series into our computation to take the piece which started as e to the x when we began to compute the remainder. So I'm losing the ability to talk. E to the x, we were able to bring in our knowledge of that particular Taylor series to take that exponential, replace it with its Taylor series expression that kind of converts it into a polynomial. Taylor series, like for e to the x, it's not a polynomial, but it gives us the right kind of pieces up to some choice of order that we make so that we could simplify from there. And then this, I just wanted to remind you of what Peano's form of the remainder for Taylor's theorem looks like. And because our function is nicely twice differentiable, it did satisfy the desired limit. Okay, I'm running out of my ability to talk, so I will just go ahead and wrap it up there. I hope you enjoyed this example and that it puts you in the right position to compute other types of Taylor series computations. So thank you for your attention.